In this video, we'll take a look at section 11.3, Contingency Tables. A definition: a contingency table is a table consisting of frequency counts of categorical data corresponding to two different variables. One variable to categorize rows and a second to categorize columns. In a test of independence, we test the null hypothesis that in a contingency table, the row and column variables are independent. That is, there's no dependency between row and column variable. So our objective and our values that we use are notation. We're going to learn how to conduct a hypothesis test for independence in a contingency table. O represents observed frequencies. E represents expected frequency in a particular cell, and it's found by assuming row and column variables are independent. R represents number of rows, and then C represents number of columns. So in our example, does the choice of treatment affect success? In this table, we have a choice of treatment for, we're studying the successes with different treatments for a stress fracture. So on surgery, there were 54 successes, 12 failures. Weight-bearing cast, 41 successes, 51 failures. Non-weight-bearing and non-weight-bearing cast for less than 6 weeks. Then the first thing we do is check and see if the requirements listed below are satisfied. So the first one is that the sample data are randomly selected. Second, the sample data represented as frequency counts in a two-way table. And then 3, for every cell in the contingency table, the expected frequency is at least 5. So our table does satisfy those requirements. In this case, the null and alternative hypothesis is that the row and column variables are independent, or alternative, they are dependent. And our test statistic, we are not going to hand calculate, but it is the same as it was for the goodness of fit. Observed minus expected squared over expected. And in this case, expected is row total times column total divided by grand total. Both the TI 83 and 84 calculators perform this test, so there are no hand calculations that need to be done. Alright, so our null hypothesis is success is independent of treatment. Alternative is success and the treatment are dependent. So that says that the success rates up here would be about the same for any of these treatments for the null hypothesis. The alternative says that maybe one's better than the others. Alright, so here's how we use the calculator. This is wonderful. We're going to take, notice it's not just a row or it's not just a single list of data. We actually have rows and columns. So on our TI calculator, the test statistic and p-value are going to be generated by running the test on the calculator. So our first step is enter the values in the contingency table in a matrix in the calculator. Okay, and here's how we find the matrix. We hit the second, let me turn it on, clear out what I had. Second, and then the x to the -1 key has matrix written above it. And then we're going to arrow over to edit. And we're going to select matrix A for this example. So we hit enter. For our example, we have 4 rows and 2 columns. So we type in a 4, enter a 4 by 2. And then what we want to do is enter the specific values from our contingency table in here. So let me arrow back up and get those. So what we're going to type in the first is 54. And as you hit enter, it'll move to the next space in the row. 12, 41, 51, 70, 3, 17, and 5. So we have our items stored in matrix A. Then to get out of the matrix, you hit second and then hit the mode key for quit. It'll stay, all your data will stay in the matrix, but it will get you out of the matrix package. Because if you try to type something in, it'll try to type it in the matrix. So second mode will quit and get you out of the package. Alright, now that we're down, we've got our items listed in matrix A. Step 2, we go to Stat, tests, arrow down to chi-squared, and both the TI-83 and the 84 have this test, chi-squared test. Hit enter. It says that our observed values are in matrix A, that's where we put them. The expected values, we don't have to enter in matrix B. The calculator is going to do all the work for us and then put the expected values into matrix B for us. So we go down to calculate, hit enter. So it already takes care of the formula. Our chi-squared, our test statistic, chi-squared, is 58.39, and our p-value is 1.29 times 10 to the negative 12, which is close enough to call it 0. The degrees of freedom excuse me, are calculated by the calculator, but what degrees of freedom are for contingency tables are the number of rows minus 1 times the number of columns minus 1, which in this case we have 4 rows and 2 columns, so it's 3 times 1 for degrees of freedom. So our conclusion, since the p-value is so low, we reject the null. It appears that success is dependent on the treatment. And then although the results of the test don't tell us which treatment is best, you can look at the success rates and you can calculate those by looking at the table. Take the number of successes for each treatment divided by the total. If you do that, it suggests that the best treatment is to use a non-weight-bearing cast for 6 weeks, because we've had 70 successes, 3 failures, so 70 divided by total 73.959. That has a 95.9% success rate.